In this video, we're going to analyze a particular sort of product that shows up in geometric algebra, namely the vector-bivector product. And what we're going to do is first review the geometric algebra 3 dimensions, G3. We're going to then cover this vector-bivector product. We're going to notice the parts of the product according to its grades. And then we're going to extend our concepts of the dot product and the wedge products. And then we're going to give a geometric meaning to these extended dot and wedge products. In the last video, we put in our work setting up the basis for G3, and let me briefly review the sorts of objects we have in our basis. We started with the vectors. We had 3 of those, E1, E2, and E3, and those are represented as they normally are in 3 dimensions. Here's E1, E2, and E3. These vectors are mutually orthogonal, and they are also all of length 1. So those are grade 1 objects. Descending in our hierarchy, we have the grade 0 objects, the scalars. Those are just numbers, if you recall. And we represent these geometrically by points. And then we form the grade 2 objects by wedging any 2 of these 3 vectors together. If we wedge E1 and E2 together, we get E1, E2. Geometrically, that's the wedging of E1 and E2, which forms that oriented patch of area. Then if I choose to wedge E2 and E3 together, I get E2, E3. That's represented here, E2, wedge E3. And then finally, I have the last combination of wedging E3 and E1. And that's wedging E3 and E1 right there. So I have my 3 bivectors in my basis. I also introduced the term pseudo-vector for these quantities, but I'll also call them bivectors. And then our last object, the trivectors, the grade 3 objects, that was obtained by wedging all 3 vectors together to form E1, E2, E3. And remember what the geometric interpretation for that was. We have E1 wedge E2, that forms that oriented patch of area. And then we extend that area, in the sense of extension along the wedge product, along the E3 direction. And what that forms is a oriented volume element. Besides the particular elements in the basis, we also had a number of algebraic properties which we've been developing in this video series. Let me briefly remind you what those are. We have that each one of the vectors squares to +1. That is E1 squared, E2 squared, and E3 squared. Those are all 1. And furthermore, we found that when we have something like E1 and E2, we can flip the order to write E2, E1. We just have to stick in a minus sign. To take a particular example, E1, E2 is equal to the negative of E2, E1. More generally, if we have EI times EJ, when I is not equal to j, these 2 indices are different, we write that as minus EJ times EI. And from these, we have a few properties that we can derive too. We also found that all of these bivectors square to -1, and this trivector also squares to -1. Those algebraic rules are important to keep in mind because if I ask you to calculate the product of any 2 linear combinations of these basis elements, that is the product of any 2 multivectors, you're all set. You just follow the rules. For example, if I ask you to calculate 2 plus E2 plus E3, just making up some random multivectors, and let's multiply that by, let's say, E3, E1 plus E1, E2, E3. What you do is you just distribute, follow those algebraic rules, and you'll get some other multivector as a result. Some other linear combination of these 8 basis elements. So we're doing quite well on the computational side. Now it's just a matter of trying to understand what these particular geometric products mean. So let's kind of review the possible geometric products of these elements that we could possibly encounter. So we could have a scalar times any one of these other 3 grades, in which case that's pretty simple, you just scale it up. Now I could multiply a vector by another vector, but that's a case we've already talked quite a bit about. For example, if I have 2 vectors, let's say u and v, I take the geometric product uv. What happens there? Well, you get a scalar part, a grade 0 part, u dot v, and then you get a grade 2 part, which is u wedge v. So when you multiply a vector by a vector, you get a grade 0 part and a grade 2 part. So that case is covered. Now, the case I'd like to talk a bit about in this video is the product between a vector and a bivector. So I'll leave that aside. Another sort of product you could imagine having is a product between a bivector and another bivector. And that's going to be its own separate topic, but if you want to explore a little, see if you can discover things, then go right ahead. And another topic unto itself is the product of a trivector, or the pseudoscalar, times these other three grades. That's going to be its own topic. So that covers really all the cases. So let's get right into talking what happens when we have a product of a vector times a bivector under the geometric product. What happens then? To understand what's going on with this vector-bivector product, we're going to deal with many simple examples and then try to work our way up to generalities. And of course, we're going to draw some pictures along the way. So the particular example I'd like to start off with is the vector e1 plus e2 plus e3. Let me call that A, and let's draw it in on the picture here. So it's a sum of e1 and e2. So let me draw on that sum there. And then I'm going to have to go up in e1. So A is going to look something like this. And of course, you got to think of this in 3 dimensions now. So there's my vector A. And the bivector I'd like to consider, another simple one, that's just going to be e1, e2, which is equal to e1 wedge e2, because e1 and e2 are orthogonal. And again, let's draw that into the diagram here. So I'm just wedging e1 and e2 together, forming that parallelogram. I'll stick the orientation symbol on there. So I have my vector there, and you can see the vectors above the plane of this bivector. I have that vector A, and I have the bivector B there. And now I'm going to do exactly what I said I was going to do. I'm going to multiply those two together. So it's going to be equal to e1, e2, e3, e1 plus e3, times e1, e2. And again, let's just follow the rules. We distribute the bivector to each of the 3 terms. We have e1, e1, e2, plus e2, e1, e2, plus e3, e1, e2. e1 squares to 1, so those go away, leaving me with e2. Now I'm going to switch the order of these two. I'm going to bring this to the front. So that's one swap, an odd number of swaps. I'm going to stick in one minus sign. So it's going to be minus e1. And then what I'm going to do is I'm going to shuffle this e3 over 2 places. So you stick in 2 minus signs, which is just a plus sign. So that's going to be equal to plus e1, e2, e3. So let's observe what's going on here. We have the product of a grade 1 element and of a grade 2 element. And what happens when we consider AB? What we're left with is a vector part, a grade 1 part, and we're left with a grade 3 part, a trivector part. So that's an important observation, that this geometric product between vector and bivector splits into a grade 1 part and a grade 3 part. And at this point, I'd like to introduce a piece of notation that's going to accentuate that splitting into grades. What I'm going to say is that this first vector part, minus e1 plus e2, is equal to, and here's a piece of notation, the grade 1 part of AB. And what I just said, the grade 1 part is going to be symbolized like this with these angled brackets here. And that number down there indicates the grade that I'm talking about. And correspondingly, the grade 3 part of AB is going to be symbolized like this. E1, E2, E3 is equal to the grade 3 part of AB. And again, with those angled brackets and the 3 denoting the grade 3 part. So these angle brackets just mean take the grade whatever part. And to drive home this concept of splitting the geometric product into parts, let's review another case that we're already quite familiar with, that I was talking about in the beginning part of this video. Let's say I have 2 vectors, u and v. That splits into a grade 0 part and a grade 2 part. The grade 0 part, the scalar part, I'll write as the grade 0 part of uv plus the grade 2 part of uv. So it has grade 0 parts and grade 2 parts only. And when u and v were vectors, this grade 0 part, that is the grade 0 part of uv, is simply the dot product between u and v. And the grade 2 part was equal to that wedge product. So with this new piece of notation, what I could say about this vector-bivector product is the following. A times big B where A is understood to be a vector and B is understood to be a bivector, that splits into a grade 1 part, that's that vector part, that thing in this particular example, and a grade 3 part. So that's grade 3 part of AB. Now, when we were dealing with the geometric product between two vectors, we found that that grade 0 part, the scalar part, that is the dot product, that had a special property in that it was commutative. And the grade 2 part, the wedge product part, had another special property in that it was anti-commutative. Now, to discover what the properties of these, well, let's suppose they do have any properties of these grade 1 and grade 3 parts, let's try to play the same game. Instead of considering A times B, let's consider B times A. Let's consider instead the product between bivector and vector. So in this example, we have E1, E2, plus E1 plus E2 plus E3. So let's just do the calculation and see what happens. So we have E1, E2, E1, E1, E2, E1, plus E1, E2, E2, and finally E1, E2, E3. Let's have a look here. So what I'm going to do is I'm going to move this over here. So it's one swap. So I guess taking one minus sign. I'm going to be left with minus E2. E2 squares to plus 1. So I'm left with plus E1. And then there's not much I can do with that. So plus E1, E2, E3. So again, we find that BA, the bivector-vector product, splits into a grade 1 part, a vector part. There's the vector part. And a trivector part, or grade 3 part. So again, we see this splitting into grade 1 and grade 3. But let's have a look. Let's compare the grade 1 elements here. Here we have minus E1 plus E2. Here we have plus E1 minus E2. So we notice that the grade 1 parts are actually opposites of each other. And what do we notice about the grade 3 parts? They're the same. So let's write that out. So we said that the grade 1 part of BA is equal to the opposite of the grade 1 part of AB. And that would be notated like this. And we also found that the grade 3 part of BA is the same as the grade 3 part of AB. So that's another pretty important observation there, that when you flip the order of the geometric product, instead of considering AB, you consider BA, the vector part flips sign. So the vector part, in this case, the lower grade part, is actually the anti-commutative part of this geometric product. And then when you flip the order, you get no change in the trivector part. So we have those two observations. And we had this other observation that AB generally splits into a vector part and the trivector part. Now you may object that we were only considering one example, but what I'd like you to do as an exercise is to verify that these three statements are always true for any arbitrary vector times any arbitrary bivector. And let me set up that statement. So let's say we had A times B. Let's say that's equal to A1 E1 plus A2 E2 plus A3 E3, where the A1, A2, and A3 are just some scalars. So this is just some arbitrary vector times, we're going to write some arbitrary bivector. So this could be little b1, E1, E2, plus B2, E2, E3, plus B3, E3, E1. So this is just a pretty simple computation. You just distribute, follow the algebraic rules, and you'll indeed discover that this product splits into a vector part and a trivector part. And when you flip the order, instead of considering A times B, when you consider B times A, that is this times this, these two statements will also be true. However, even before you do this computation, hopefully you can sort of think through why this happens at all, why you get a grade 1 part and a grade 3 part. For example, if you consider E1 and how it gets distributed to each of these three bivectors, in two of these bivectors, the E1 is already there. So after you do a little swapping, put in a minus sign if you have to, you're left with the other vector. And what you get from that multiplication makes a contribution to the vector part. And then in that last case, where E1 is not present, that is E2, E3, that product will make a contribution to the trivector part. And you can run the same argument for the E2 part of this sum and the E3 part. You either get a contribution to the vector part or to the trivector part. So let's review what we've discovered. If we have a vector A and a bivector B, that can be split into a grade 1 part, a vector part, and a trivector part, grade 3 part. And then we also consider that product, the commuted product, BA. Again, where B is a bivector and A is a vector. And that can also be split into a vector part and a trivector part, BA 3. But what we notice is that this vector part has a special relation to this vector part, and the same for this trivector with this trivector part. That is, this vector part just so happened to be equal to the opposite of this one. And this trivector part happened to be identical to that trivector part of AB. So I can rewrite the statement as BA is equal to minus the grade 1 part of AB plus the grade 3 part of AB. Now here's a little magic we can do when looking at this line and this line. And what we're going to do is we're going to attempt to isolate the grade 1 part of AB. And here's what I'm going to do. I'm going to take this line and subtract this line. So on the left hand side I'm going to have AB minus BA. AB minus BA is equal to the grade 1 part of AB minus the grade 1 part of AB. So I get 2 copies of the grade 1 part of AB. Then I'll have the grade 3 part of AB minus the grade 3 part of AB. So that's 0. And now I just simply divide by 2. And what I can write is that the grade 1 part of AB is equal to 1/2 AB minus BA. And this is pretty interesting too, because this looks very similar to the wedge product formula between two vectors, written in terms of the geometric product. And you can see that has that minus sign there, which means that this thing is anti-commutative, which is what we already know. And now what we can do is play a similar game to isolate out the grade 3 part of AB. What I'm going to do is, instead of subtracting, I'm going to take this line and add it to this line. So on the left hand side, I'm going to have AB plus BA. So AB plus BA is equal to the sum of the grade 1 part of AB and of the minus grade 1 part of AB, so that's 0. And I get the grade 3 part of AB plus the grade 3 part of AB, so that's 2 times the grade 3 part of AB. And again, I divide both sides by 2, and what I could say is that the grade 3 part of AB is equal to 1/2 AB plus BA. And notice this is similar to the dot product formula between two vectors, which we found was commutative. And correspondingly, we found that this is commutative when we swap the order of A and B. The trivector part stays the same. So we're actually getting a flipping of the roles here. The lower grade part in this thing is the anti-commutative part, and the higher grade part of AB is actually the commutative one. So here's perhaps the key definition of this video. I'm going to look at this vector part of AB, and I'm going to call it the dot product between the vector A and the bivector B. So that might seem a little bit odd at first, taking a dot product between vector and bivector, but this is going to very nicely extend our concept of the dot product. So if I call the lower grade part the dot product between A and B, what should I call the higher grade part? Well, I'm going to call that the wedge product between the vector A and the bivector B. So here are the two key definitions of this video. We have an extended concept of the dot product between vector and bivector, which was simply that grade 1 part of AB, and an extended concept of the wedge product between A and B, which was the trivector part of AB. So in this definition of the dot product between vector and bivector, we notice that minus sign there, and what that's going to translate to is saying that the dot product between vector and bivector is actually anti-commutative. Now that might seem a little bit odd because we know that the dot product between two vectors is actually commutative. And correspondingly, when we wrote the dot product between two vectors in terms of the geometric product, we actually had the plus sign there. So that's why it was commutative. Correspondingly, when we were talking about the case between two vectors, we found that the wedge product was anti-commutative. And that corresponds to a minus sign in the expression involving the geometric product. But here we notice a plus sign. So what that actually means is that A wedge B is equal to B wedge A. So you're allowed to flip vector and bivector like this without a sign flip. But if you want to swap A and B under the dot product, here's where you're going to have to stick a minus sign. But what's also nice about defining the dot product and the wedge product of these two the grade 1 part and the grade 3 part is that if we just consider the geometric product between a vector and a bivector, we can also write this as a dot product part plus a wedge product part, just like we had between two vectors. Remember, we had, if we just had uv, where u and v are two vectors, we have a lower grade part. In this case, this is a grade 0 part compared to the grade 1 part, plus a grade 2 part. Here it was grade 2, and here it's grade 3 for the higher grade. But what I'd like you to notice most of all is a conceptual unification of the dot product as a grade lowering operation and the wedge product as a grade increasing operation. If we go back to the case between two vectors, the dot product lowers the grade of this vector v, which is grade 1, by 1 to a grade 0 element. And the wedge product increases the grade of v to 2. So that's the grade 2 element there. If we take the same point of view, starting with b, which is a grade 2 element, the dot product decreases it to a grade 1. So here's the vector part. And then the wedge product increases it to a grade 3 part, a trivector part. So again, the dot product is the grade lowering operation, and the wedge product is the grade raising operation. Let me make a quick note about the wedge product E1, wedge E2, wedge E3. And remember in the previous video we used this to set up the trivector element, E1 times E2 times E3. But let me show you how this extended concept of the wedge product fits in nicely. So first we take E1 and wedge it with E2. We already know that's just equal to E1, E2, which is a bivector now. Now I wedge that with the vector E3. So this is perfect. It fits into our definition nicely. And according to the definition, this is the grade 3 part of the geometric product between E1, E2 and the vector E3. And you just take a look. That geometric product is only a grade 3 part. So this is E1, E2, E3. So we have, as we expected, E1 wedge E2 wedge E3 is equal to E1 times E2 times E3.